Okay, guys, so the second last section in chapter 8, let's talk about hyperbolas. This is the fourth conic section we've talked about. The first one we spoke about was a parabola. Second one was a circle. Third one was an ellipse. And today we talk about hyperbolas, the fourth one. Okay, so hyperbola looks like this. Now, we've done hyperbolas before in chapter 5 when we did inverse variation, but these are a little bit different. We did general rational functions and all kinds of very, very complicated rational functions. But here we're sticking to the conic section that makes a hyperbola, and that has a very different set of rules and equation. Okay. And I will say this, please, you'll see down here on the note sheet, I say list some applications of hyperbolas discussed in class. Obviously, we're not in class. All four of these conic sections really are amazing, amazing gifts to us to be able to understand the world and the structure of certain things. And, you know, it's really, really amazing. They're used for so many things. I think I discussed a few of the uses of a parabola with you. Not so much a circle, not so much as an ellipse. And I'm not going to talk about hyperbolas in this video. I think what I'm going to do, usually in class I spend 20-30 minutes going over each conic section's applications and I show pictures and things like that. I think what I'm going to do is not do this on this note sheet today. But I'm going to make a separate video that I'll be posting for you that I talk about all the applications of all the conic sections. And that'll be mainly me showing you pictures and links to websites and things like that, where we go over how do people actually use conic sections in the real world, that you understand we're not just doing this to waste your time and play with equations, okay? I do enjoy playing with equations, I know some of you do, but it's not really the reason why we're learning about conic sections. They're used a lot to influence structure of construction, things like that all the time, for medical treatments, satellite communication, all those kind of things. Conic sections are huge in the world around us, and in engineering and math and science and the medical field, all kinds of things. Okay, so having said that, let's just jump in here and do hyperbolas today. All right, so I made a separate video about this, which is the definition of hyperbola. And so please go watch that. I've posted that already. And then we'll talk about just how to do the tasks that we're asked to do. Graph hyperbolas, write equations of them, and then solve some problems using hyperbolas. Okay? So the line through the foci. So hyperbola has two foci. So here's a focus and here's another one. So the line through the foci, which that would be the x-axis in this case, intersects the hyperbola at the two vertices. All right, so we would call these 2 points here vertices. Okay, and then the transverse axis joins the vertices. So just like an ellipse, we had an ellipse here, we had a vertex here, with a vertex here, with a focus and a focus. And then we had a line that joined the two vertices, and we called that an ellipse. We called that the major axis. Well, here we're calling this axis right here that joins the two vertices, that's called the transverse axis. Okay, the transverse axis. Again, there's a transverse axis that joins the two vertices, and if you drew a line through that, on that same line will be the foci. Okay, and then also maybe I should use a different color here. Right in the middle, this is the center. That's the center of the hyperbola, and if it's the center of the hyperbola, it means the distance from here to the center and from here to the center. Those are the same. Okay, those are the same. And also, please notice something. I think we're going to use it for our problem solving later, but hyperbola is also symmetric. So just like we had parabolas being symmetric about the x-axis, a hyperbola is symmetric about its transverse axis. Okay, so whatever the transverse axis is, or the line through the transverse axis, this distance from here to here is the same as the distance from here to the corresponding point at the same x-coordinate. Okay, so there's some symmetry there, and we actually talk about symmetry a lot more next section. Okay, so we'll talk about that again. And then a hyperbola has two branches, so here's a branch and here's another branch. We discussed that before. And it also has two asymptotes that contain the diagonals of a rectangle centered at the hyperbola's center as shown. Okay, so you'll see, this is not too bad. This whole sentence here that seems terrifying, it's not too bad. What it's saying is, there are two asymptotes. Here are the asymptotes. Okay, there's one. And then here's another one. I apologize for going off the line there. Those are the two asymptotes, and they contain the diagonals of this rectangle. Okay, so you'll see the way we're actually going to draw our hyperbolas is to first we're going to draw the rectangle. Okay, and then we're going to say, oh, the asymptote just goes through the two corners of the rectangle, and the other asymptote goes through these two corners, and then you end up getting the two asymptotes that tell you what the shape of the branches need to look like. They approach the asymptotes. Okay, so that's actually how we're going to end up drawing this. So this sentence seems really bad, the last one there, but it's not too bad. Okay, and then again, please, as with an ellipse, the letter A is associated with the vertex. Okay, and in an ellipse, the letter B is associated with a co-vertex. This is not called a co-vertex, but it is an important point for us to be able to draw the box that gives us the diagonals that form the asymptotes. Okay, so it's a very important point for us, this point B here. As you can see in your equation, it's going to be the thing behind the minus, but it's not called, it doesn't have a name per se. Okay, so the letter A still goes with vertex, the letter C still goes with focus, just like an ellipse, and the letter B just helps us draw the box that helps us draw our asymptotes. Okay, it gives us the slope of the asymptote. All right. So, two things you have to notice. Of course, there are two different ones, this one and this one, and you'll see. Wait, what's different? Well, here x squared is in front of the minus sign, and the number underneath x squared here is called a squared. And if you look at it, the transverse axis is in the x direction, it's horizontal, and the foci are also on the line going through that. In this case, because for section 8.5, all of our hyperbolas are still centered at the origin, it is the x-axis. Okay, so our hyperbola is horizontal because x squared is in front of the minus sign. Okay, and then a tells me, then this number underneath x squared is a, and it tells me where the vertices of the hyperbola are. Okay, in this case, over here, we have the hyperbola is vertical because the transverse axis is basically on the y-axis in this case, since the origin is still the center, and the foci are also on that y-axis, and you can see that because y is in front of the minus. Okay, so unlike an ellipse, in an ellipse equation, let me just write that out for you here, we had stuff like this happening, x squared over a squared plus y squared over b squared equals 1. It looks very similar, but it's not quite the same. Or we could have x squared over b squared plus y squared over a squared equals 1. This ellipse, if the way this worked was, a is always bigger, okay? And so this told me that since a, the bigger number, is under x, this would be a horizontal ellipse. And here, since a is bigger and it's under y, this would be a vertical ellipse. Okay? Well, here, for hyperbolas, it doesn't work that way. For hyperbolas, how it works is, since the x squared is in front of the minus, then the hyperbola goes in the x direction. So it's a horizontal hyperbola. here, since the y squared goes in front of the minus, then it's a vertical hyperbola, and the transverse axis is in the y direction. Okay, so it's a bit different between an ellipse and hyperbola. Those are not quite the same thing. Okay, so that's the difference there, but it's not really too terrible to deal with. Then, so standard equations. Again, if x squared is in front of the minus, then it's a horizontal hyperbola. And here are the asymptotes. Now the asymptotes, since ours hyperbolas are centered at the origin, you could really just count the rise and run to find your asymptote equations. Okay. Now I'm not sure if we're going to actually require you to do this on a test or not, but to find the equation of the asymptote in case of a horizontal hyperbola like this one, you can really just say I rise b units and run a units. Okay, so rise is b and run is a, and that's the slope. Because there's no y-intercept, the y-intercept is 0, so you have plus 0 here, so we don't write that. Okay, so it's not really that difficult to come up with what the asymptotes are. It's just basically, you don't have to memorize this. You just say, what is the asymptote? Well, one is rise b, run a, and the other one is rise negative b and run a. Okay, so that's why you have the plus minus b over ax there. That's not too important that you memorize that. I think you can just write it from here. Okay, it gets harder when the center of the hyperbola is not the origin. Then this becomes a bit tricky, but for now it's not too difficult. Okay, and vertices, once you have the vertex, you can write the coordinate points. We don't really require you too much to do that. But then you have to ask yourself, okay, again, just like for an ellipse, the equation of hyperbola has an a and a b. The a is the vertex and the b is the sort of air quote co-vertex thing that helps me draw the box to make the asymptotes. So how do I get c? Because there's still a focus, and focus is still associated with letter c. How do I get that? Well, we had a formula for ellipses. The formula for ellipses were c squared equals a squared minus b squared. A was always bigger than b, and you got some number. Okay. In this case, for a hyperbola, it's actually a plus. Okay. So think about it this way. Let me write this again. X squared over a squared plus y squared over b squared equals 1. So this is an ellipse formula. Okay. So for the formula of an ellipse, the formula itself has a plus, and therefore the corresponding equation to find the focus is a minus. Okay. For a hyperbola, the formula, as you can see, contains a minus, and then the corresponding formula to find the focus contains a plus. Okay, so they're opposite. So if this is your formula you're working with, then you know that I'm subtracting to find my focus. If you're working with a hyperbola and the formula is a minus, then you know I'm adding to find my focus. Okay, there's a little bit of memorization there. And again, please remember, this is not really the best way to learn this. The best way to learn this is to prove everything to yourself. But the proofs here, or not even proofs, just deriving the formulas and things like this formula, it gets quite tedious, as in 1 or 2 pages long. And so we're not doing that here. We do it as much as we can. We tried in this section, in this chapter, as much as we can to do that, but we can't do that here, okay? So there's an element of just memorize that, and maybe just memorize the form, because we didn't derive those formulas. Okay? And I think I do have a derivation of this formula posted in online, so you can go find that if you really are interested. It's probably worth a read if you like mathematics. Okay? Alright, so example 1. I don't think I'll do the whole of example 1 because there's 4 graphs. That's a bit much for this one video. I'll just do maybe 2 of them. And then you can do the other 2 if you want. You can go look at the note sheet. Okay? And so let's see what we have going here. So maybe I think maybe what I'll do is, which 2 should I do? Maybe I will do letter B and letter D. Okay, I'll maybe do letter B and letter D. Let me just talk about letter A as well. So notice we were just talking about the formula and thing, and here's the formula, okay, of the two different types of hyperbola, horizontal and vertical. And then you look here and you go, wait, neither of these look like that. What's the deal? Okay, so yeah, you have to make them look like that. You have to make them look like that. Now, there's a bit of a weirdness here. So I'm going to do letter B with you completely, but let's look at letter A. This is much like one of the ellipse examples we did. I need to make the equation equal to 1, not 100. Okay? And so what you do to make it equal to 1 is just divide by 100 here, divide by 100 here, divide by 100 here. And then it's fairly easy after that. 4 divides by itself, 4 divides by itself, 25. 25 goes into itself once, and here 4. And so you quickly end up with this for your hyperbola equation. Okay? Now, that's fairly simple. This then letter B is a bit tricky. So I did want to show you this, but you have it now. There you go. Congratulations, we wrote it. Whether you graph that or not is up to you. But letter B is slightly more tricky, so that's why I wanted to do this one with you. Okay, so letter B, again, I want this to be 1. So how do I go about that? Well, divide by 9. Okay, and so far so good. That seems okay, but please, this doesn't look like the standard form of a hyperbola. X squared over 9 minus 4y squared over 9 equals 1. That doesn't look right, okay? I can't have like numbers up here by the y or the x, on top in the numerator after the minus sign. So that's not really correct. So what you have to do is somehow divide this so I get rid of all that stuff, okay? And so what you end up doing is something interesting. So how can I get rid of the 4? Let me zoom in here. How can I get rid of the 4? You do this. You say if I multiply by a 4th, top and bottom, okay, then this will cancel and it becomes a 1. And then on bottom I get 9 times 1 over 4. Okay, so actually if you do this you get x squared over 9 minus, this is now a 1, okay, so y squared over, and then you get 9 over 4 equals 1. That's a bit tricky. Yeah, that's a bit tricky. But just notice, I must have a 1 for my coefficient in the numerators here. Otherwise, I'm not really drawing a hyperbola in the standard form that works for our methodology. Okay? So, after all that's said and done, here is the actual standard form that we're going to be looking at. Okay? And now we can just proceed and do what we normally do here. So, remember, in this case, a is always, or a squared, sorry, is always the denominator of the fraction in front of the minus. And so this would be my b squared. Okay, so remember, look at here, a squared is always the denominator of the first fraction in front of the minus. Okay, and b squared is always the denominator of the second fraction after the minus, and the variable that's in front of the minus tells me the orientation of the hyperbola. So I know already this hyperbola is going in the x direction. It's a horizontal hyperbola, and the transverse axis will be on the x-axis in this case. Please remember, for this section again, 8.5, all our hyperbolas are centered at the origin, so there's the center. Okay, and you'll see this from the equation as soon as we do section 8.6. So now what do? Okay, so I know that the vertex is a units away from the center, so I just have to find a. Well, we just wrote up here that a squared is 9, so you can do a squared is 9, therefore a is plus minus 3. So from the center, I go 1, 2, 3 units to the right, and this is my vertex, okay? Let me write vertex here. And then I go 3 units to the left, and this is my other vertex, okay? So we know that this is the transverse axis, all right? And I'm expecting the foci to be somewhere here as well on the line that goes through the transverse axis, through the vertices, okay? But that doesn't help me yet. I did something great. Now I know that if this is a vertex, the branches will look something like this. It will be horizontal because the x term is in front of the minus again, okay? But that's not good enough. How do I draw the shape? I can't really just do that. So that's where you use b. We used a, check, so now we have to use b, and we say b squared is 9 over 4. And so if I take the square root both sides, b is plus or minus square root of that would be 3 over 2. Okay, 3 over 2. So 3/2, or 1.5 if you'd like it that way, to graph. Okay, so 1.5. So what I do here now is I say b is 1.5, which would be over here. But we don't name that point because it's not a covertex, it's just a point that helps us draw the asymptotes. Okay, it's just the strategy we use. And then what you do is just draw the box now. Okay, so these 4 points form a rectangle that I can use to draw my asymptotes. Okay, so we're basically doing this, all of this, just so that I can draw the rectangle that contains that helps me draw my asymptotes. Okay, so we have that. So now I'm going to draw the asymptotes using the little box. And so it's these 4 corners that help me draw my asymptotes. Okay, and so the asymptote just goes from the center through the corner of the box. Okay, and please, of course, it doesn't have to be perfect because it can't be perfect at this point. We're not computers. Okay, so you do something like that. All right. Now a lot of students make a mistake here. Please, do you see what I did? I labeled vertex here. All right, and vertex here. The red dots there are the vertices. And this is not a co-vertex, so I don't do anything here. Okay, just help me draw the box. So now I can already draw the hyperbola. The hyperbola looks like this. Okay, an asymptote, we said, we define that as a line that the function or the curve approaches more and more closely. Okay, so that is what we define an asymptote as, and that's what must happen. Please, students draw some strange things sometimes, like hyperbola crossing the asymptote and stuff. You can't do that. You're going to lose points for that. That means you don't understand what you're doing. All right, so the hyperbola must just approach the asymptote more and more closely. Okay, also please don't draw stuff like this. This is not correct, okay? And then the other thing students do sometimes is, instead of drawing the branches from the vertices, they draw the branches from here. Okay, now I understand at this point maybe if you want to make that mistake. I kind of get that right now, but you notice that we drew the vertices here and the transverse axis. Okay, so that tells me the direction and where the branches have to go. And more importantly, we still have to find the foci. We didn't find the foci. So the formula we said is c squared equals a squared plus b squared in this case. Remember from here, c squared equals a squared plus b squared. Okay, and so what we're doing is plugging this in and finding the foci. We didn't even draw the foci yet. So c squared equals a squared is 9 and b squared is 9 over 4. Okay, so if you do the math there, you convert this, you get 36 over 4 plus 9 over 4, you get 45 over 4. Okay, and then that means that c is plus or minus root 45 over 4. That's irrational. Make it a decimal on your calculator, you get plus minus 3.4, something like that, 3.4. Okay, and so what we're saying is the foci are 3.4 away from the center. Okay, so 1, 2, 3.4, maybe about here. That's a focus, and then maybe about here. That's another focus. Okay, Now, please remember, if you remember how an ellipse, I mean a hyperbola and an ellipse, but how a hyperbola is formed, the definition for the conic sections was it relies on the foci. Okay, so again, you can't draw a hyperbola without the foci. Otherwise, you're just making up stuff. Okay, the hyperbola completely depends on the foci for its existence. If we're talking about conic sections, okay? And so remember, it must look like this, must look like this, and there, because also the hyperbola's branches must embrace the focus, okay? The focus is always inside the conic sections. Remember, for an ellipse, the foci are here. For a parabola, the focus is here. For a hyperbola, the foci are inside. There's all of these conic sections contain or embrace, or whatever you want to call it, the foci. So you should know that you shouldn't be drawing branches up here. That's totally out of place because there's no foci, and there's no transverse axis. It doesn't make any sense. Okay. All right. So that's really all you need to draw a hyperbola. What I do in my completed note sheet is do a lot more work labeling things, foci and vertices and things. I think what you at least have to do is at least label F for focus, V for vertex here, and then maybe you can put C for center here. So at least we know just by looking at your sketch very quickly that you know what you're doing, okay? And that these numbers are not just meaningless math floating around, that we can see, oh, that's how the vertex came about, oh, that's how this came about, and oh, this is where your focus comes from, okay? So, yeah, so that's about that. So I did the one horizontal hyperbola here with you, letter B. It's a little bit more tricky because we have to also wrestle with the equation a little bit. You can see that these two are already in standard form. Okay, so I don't really have to wrestle with that too much. So it's a little bit easier, we can just graph it. So I'm going to do letter D with you. And then again, please, the completed note sheets. This is done, and this is done, so you can go check it, check yourself, and do those if you want. All right? So letter D is already in standard form. So again, I'm going to write the standard form, y squared over a squared minus x squared over b squared equals 1. And so I know that this is a squared, and I know that this is b squared. What's b squared? B squared is 1. Okay? And so all I need to do now is draw things. You should know that because y squared is in front of the minus, it's the term in the front of the minus, or it's the first fraction. Therefore, my transverse axis is going to be vertical. So I'm expecting this type of hyperbola, as opposed to here, x squared was in the front, so I'm expecting a horizontal parabola, not parabola, sorry, hyperbola. And so same thing here, but because y is in the first fraction has y squared, therefore it's going to be a vertical hyperbola. All right, and so I'm doing this. We're doing center. We know is here again. Okay, and then we know it's a vertical hyperbola, so I'm expecting the vertices to be this way and the transverse axis. And so I do a squared equals 36, and that means a is plus minus 6. So I'm going this way 6 units. Okay, and then I'm going down 6 units. And these are my two vertices. Okay, label them, vertex, and label this center, please. And then I know this is the transverse axis. Okay, connecting those two. And so now I know where the branches are. The branches definitely are here. Okay, they're here. And I can't draw the other point, so I can use b squared. Let me do that. So we can use b squared equals 1. That means b is, if you take the square root, plus minus 1. So 1 and 1. And now I can draw my box that will help me draw my asymptotes. Okay. And so you just do this. So we know that the corner of the box is here, the other corner is here, the other corner is here, the other corner is here. this will help me draw my asymptotes. And really, I don't know if you really have to draw the whole box in dashed lines, and that takes some time, but you know, it does help a little bit. In any case, now you have to draw your asymptotes, so let me do that very quickly. Okay, there's my one asymptote, and the other one, wow, this is quite the tricky, oh, that's completely wrong, forgive me. I didn't make my asymptote go through the center. Okay, sorry, the asymptote has to go through the center. Wow, that's tricky. That looks pretty hideous. Okay, and then we have it now. So we have the shape pretty much of my hyperbola. That's not the most attractive one, but it's good enough for our purposes here to draw the hyperbola. It must just approach the asymptotes more and more closely. Okay, so there is the hyperbola. Missing feature of my hyperbola is still the foci. I need the foci. Okay, so let me do the foci. So the foci come from c squared equals a squared plus b squared. So c squared is 36 plus 1, which is 37. And then if I say take the square root, then c is plus minus root 37, which is approximately plus minus 6.08 or something like that. Okay, that's just slightly bigger than 6. Wonder if that's right. Did I do that right? Yeah, that must be correct. Okay, so like 6.1 maybe or something. So that's very hard to draw properly. If this is 6, I mean the foci are like right there. Okay, the foci are like right there by the vertex, because the vertex is at 6 and negative 6. So the foci are very close. But please label the foci, label the vertices, label the center, show me the box, show me how you do the asymptotes. And then also, I didn't do this on this equation, but maybe we could go back and do this. This is interesting. Since these hyperbolas are centered at the origin, we can easily write the equation of the asymptotes. So the asymptotes will be where in this case? Okay, so I go up 1.5 or 3 over 2, and I go over 3. Okay, so my rise over run is up 3 over 2, and I go over 3. Okay, and so then you can use that, multiply by a third, something like this, and you get 3 over 6. So that's a half. Does that seem right? Go up 1 over 2, up 1 over 2. Yeah, that does seem right. Okay, so here's the equation: y equals plus or minus 1/2 x. Okay, because the asymptotes go through the origin, so they have no y-intercept. The y-intercept is 0, so this is it. Y equals plus or minus 1/2 x. And you could do the same here, but this may be a bit easier, because for my asymptotes here, what am I doing? Y equals plus minus something x, and what's the slope? Okay, so I rise up 6 to here. 1, 2, 3, 4, 5, 6, and then I run 1. Okay, so plus or minus 6x. Those would be my asymptotes for this graph. Alright guys, please, this is the minimum work you have to show. That's about as little as we could possibly ask you to do. If you label your picture clearly and all that work is done just like that, at least we know that you know what you're doing. Okay. Alright, then example 2 says write an equation of the hyperbola with the given foci and vertices. So you're given foci and vertices, all right, and then they say write the equation of the hyperbola. Okay, so remember, foci correspond to letter C and vertices correspond to letter A. All right, and so you can do this two ways again. You can do it purely algebraically, or you can write you can draw a picture and then try and do it from the picture. Okay. Just notice that the foci and the vertices are always together on the line that goes through the transverse axis, but they're both x coordinates in this case. And so if I have this kind of situation and my foci are at 4, -4, and my vertices are at 3, -3, like this, which means my if this is 4, -4, this is 3, sorry, -3 and 3, means my hyperbola looks like this with the transverse axis here. This picture is ugly, but that's okay because I'm not really trying to draw it. I'm just trying to solve answer the question. So I'm doing this, and then you just say, oh, I know it goes horizontally at this point because these are x coordinates. So therefore, I know this is the kind of equation I'm going to have for my hyperbola. Okay, x squared goes in the front because the foci and the vertices are x coordinates. Okay, so in other words, it looks like this. All right, it looks like this. So that's how I know which form of equation to use. And at this point, you just plug stuff in now. Again, vertices are associated with letter A, foci are associated with letter C. So I have A already, so I can do this, x squared over 3 or -3, doesn't really matter. It's 3 squared minus y squared over b squared. But the problem is I don't know b. Okay, I don't know b. So what we do is say, oh, I know C and I know A, and I have an equation that relates all this stuff. C squared equals A squared plus B squared. So I know C, which is 4, and I know A, which is 3, and I'm looking for B. Okay, so I can do this and just solve this little equation and come up with what B squared is. So I get 16 equals 9 plus B squared. If I subtract the 9, you get 7 equals B squared. Okay, so I would write B squared is just 7. Okay, so I have x squared over 9 minus y squared over 7 equals 1. And that's the equation of the hyperbola that meets those criteria. Okay, and then the other one is similar, except this time the foci, which are associated with letter A, and the vertices, which are associated with letter C, are y coordinates. You can see that these are all y coordinates, and therefore I know that my hyperbola looks something like this, and therefore I know that I have to use a formula that's this: y squared over a squared minus x squared over b squared equals 1, because the foci and vertices are on the y-axis. Okay, and same thing. I know a already. A is 10. I just want to find b squared. So I know a is 10 from here, and that means that a squared is 100. Okay. So I know this, check. I have to find b, so you do the same thing. You do c squared equals a squared plus b squared, and you plug stuff in. Now what is c? C we said is 6, so 6 squared equals 10 squared plus b squared. Alright, what does that mean? That means that did I switch that around? Oh, I switched this around. Forgive me for I've sinned. Otherwise, this would not be possible. Forgive me. The vertices are the A's, and the foci are the C's. That doesn't make sense even, because the vertex is closer than the focus to the center. Okay, and so sorry, I apologize for that. I made a little mistake there. A squared is not that. A squared is actually actually 6, so a squared is actually 36. Okay, so these two are switched around. Actually, I apologize. It should be like this. Should be c squared is 10 squared, and this would be 6 squared. So you would get 100 minus 36 equals b squared, and that would mean that b is, well, b squared, we don't want b, we just want b squared is 100 minus 36, which is 64. Okay, so I have a squared is 36, I have b squared is 64, and I can just plug them in here. Y squared over 36 minus x squared over 64 equals 1. Okay, and there's my equation of this hyperbola. All right, let me do example 3 and then I'll stop. You can do example 4, you can look at the completed note sheet. It's there. I'll just do example 3 and then at least solve this one problem with you and I'll stop, okay? Both are very, very similar, but I just don't want to make the video any longer than it has to be. It's already fairly long. Okay, so let me do example 3. It says you can take panoramic photographs using a hyperbolic mirror. All right. Light rays heading toward the focus behind the mirror are reflected to a camera position on the other focus as shown. Okay, so light rays heading towards this focus are reflected to that focus where the camera is positioned. All right. After a photograph is taken, computers can unwrap the distorted image into a 360 view. Okay. All right. Sure, they say so. Write an equation for the cross section of the mirror. Okay, so here's the mirror. I'm writing an equation for the cross section. So basically I'm writing an equation for this thing and pretending like it carries on forever, because our hyperbolas carry on forever. Okay, so write an equation for the cross section, and you were given some information. So maybe the information is not that clear sometimes to students. This distance here is 3.66, and so we're saying that from the center, now we can imagine this to be 0, 0. We can say that's the origin, okay? And then we just say that this must be distance c, okay? C units from the origin. And then from the center, and from the center to the vertex, this would be the vertex of each branch of the hyperbola would be A, right? That must be A. Okay, so they gave us C and they gave us A in the picture. So we just need to plug stuff in. Very similar to this question, they gave us C and gave us A. We just have to plug stuff in, okay? So we know already that A is 2.81 centimeters. So then what I have to do is, this is an applied problem, square both sides to get A squared. So A squared is approximately, if you square that, you get about 7.9. Alright? And then they gave us C. They said C is 3.66. So then I square both sides of this, and then I get C squared is approximately 13.4. Okay, and I'm doing this on my calculator just like you should. Alright, this is great, and I know it's a vertical hyperbola. So if it's vertical, I know that the transverse axis goes in this case the y-axis. So therefore my equation must be y squared over a squared minus x squared over b squared equals 1, because the hyperbola is a vertical hyperbola. Okay? And so all I need to now still, I have A, check, I just need B, and then I can plug stuff in and find the answer for the equation. Okay? And this is the first part of the problem. And so I would do C squared equals A squared plus B squared. Remember, the formula has a minus, so this formula has a plus. Okay? And then just plug stuff in. So 13.4 is C squared. We already found C squared. Okay? equals 7.9 plus b squared. And so if you just subtract those two, 13.4 minus 7.9, you get 5.5 is b squared. So I have all the information I need. I have a squared here and b squared here. I can just plug them in. Okay, so we say y squared like this. Let me plug them in red. A squared is 7.9 and b squared is 5.5. Alright, and so there we go. That's the equation of this hyperbola, okay, that would form both branches. And that's the equation that represents the cross-section of this mirror. Alright, so the mirror is 6 centimeters wide. So from here to here is 6. How tall is it? Okay. So here you have to remember something that I told you a bit earlier, and that is that there's symmetry here. So the distance, if I draw the line that goes through all of this, if I extend it out, okay, there's symmetry here. This distance and this distance are the same. Okay, there's symmetry there. So what I know is that this distance is 3 and this distance is 3. But that does tell me something. The 6 gives me some information. It tells me actually if the distance from here to here is 3, then it tells me that if I made this the origin at 0, 0, then the distance from here to here or here to here is 3, means that this is a point that has a x coordinate of 3 and a y coordinate of I don't know. Okay. Now, okay, that's great. I did all that stuff, but how does that help me with anything? Well, how tall is the mirror, or deep, or tall, or whatever. So the question really is, what is this distance right here? That's the question. What is this distance? Okay, that's what that question is. So, I don't know. I don't know what that is, but what we can do is say, I'm in space floating in my coordinate plane, and I have 3 is this point on the hyperbola. But I have an equation for the hyperbola that's that. And so what it means is if I have an x-coordinate for a point on the hyperbola, if I plug that x-coordinate into my hyperbola equation, then the only other unknown will be the y-coordinate. And then I can find this unknown y-coordinate. It's not really necessarily clear maybe for you why that's going to help me solve the problem, but it will. Okay, it will get us very close. So let's try that. I'm going to try and find this y coordinate right here. Okay, and what I'm going to do is say I have the equation for the hyperbola, but I'm going to say instead of writing down x squared, I'm going to plug in my x coordinate of this point right here, which is 3. 3 squared over 5.5 equals 1. Okay? And then what we're going to do is just solve that and find the y coordinate. Okay, and you'll see how this helps. So if I do this, I get something. What you get is basically y squared over 7.9 minus, if you do the math here, 9 over 5.55, you get 1.64 equals 1. Okay? And then just add this to both sides. So what you get then is y squared over 7.9 equals 2.64. Okay? And then multiply both sides by 7.9 to cancel this, then I get y squared equals 2.64 times 7.9. You get 20.5856. Okay, and then I want to find y, so you get y is equals to plus or minus, in other words, and we'll talk about that, plus or minus 4.56. Okay, so in other words, if I were to go all the way here, I would get, from the origin, I would get 4.56. but we're in the negative y-axis down here. So this coordinate down here is the minus 4.56. Okay? So minus 4.56. All right, so what does that mean, minus 4.56? That just means simply this. It means simply this, that the total distance from here to this point is 4.56. The y-coordinate is negative 4.56 because it's the negative y-axis, but that's the distance, 4.56. Okay, but that was not the question. The question was how tall is the mirror itself? Just this part. Okay, what is this distance? That was the question. So now what we have is the total distance from the x-axis to the point, and we know that the distance from the x-axis to the vertex is 2.81. So what I can do is subtract those two numbers, and then I come up with the depth, or how tall it is. Okay, I keep saying depth because that's one of the other terms we had. So if I want to know what's the distance from here to here, okay, I take the total distance from here to here, and I subtract the distance from here to here. All right, that'll give me the answer. So I'm going to do that. So how tall is it? Let's say the height is 4.56 minus 2.81, which is 1.75 centimeters. Okay, so what we're saying is from here to here is 1.75, because from here to here is 4.56, and then 1.75 plus 2.81 will give me 4.56. So this is the answer. How tall is the mirror? Okay, that's tricky. That's a very tricky question. All right, guys, I'll let you try this one, example 4. You can ask me questions about that if you want. It's on the complete note sheet. I think it's maybe a bit easier than this example. Okay, thank you.